One of the important topic in cryptography is actually primitive roots, and we want to find them specifically for prime numbers. So in this video, we will learn how to actually find primitive roots of 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 a prime number. Why do I need that? The reason I need primitive roots is to actually solve for a problem like Diffie-Hellman key exchange problem, which is a very commonly used algorithm that we use for key exchange method, and which is still being used. So in order for us to solve for Diffie-Hellman, we gotta know how to actually find primitive root of a prime number. Okay. Um I don't know. I mean, this is how I learned it, and I like this. I mean, the way I found this way is to the easiest way to actually find that. So the criteria for finding a primitive root is actually this: a number that you're trying to find. So let's say you have a number like this, um, uh, and let's, instead of n, let's just make this p. So we're trying to find a primitive root of a prime number. So the criteria that I need to have is, just first thing I need to do is actually to solve for, to find Euler-Tauschen function of that prime number. All right. So Euler-Tauschen function actually gives me the range of what numbers that I want to try. I mean, you will see as we do an example. So let's say, okay, I want to find if I have a prime is equals to 7. So in our example, so here's our example. Our prime is equals to 7, and we want to find primitive roots of 7. So the criteria is, so the Euler-Tauschen function for prime number is actually 7 minus 1. If you remember it from RSA, Euler-Tauschen function is, for RSA was, because we have to choose two prime numbers, one is p and one is q. So Euler-Tauschen function is basically prime minus 1, the second prime minus 1, and you just multiply them to get Euler-Tauschen function. Here the Euler-Tauschen function is actually just going to give me a range of numbers. So let's say, okay, in our example, we want to find primitive root of 7. So the Euler-Tauschen function for this is going to be the prime minus 1. So this is going to be 6. All right. So that's why I have 6 entries. If you can see over here, I have I is equals to 1, I is equals to 2, I is equals to 3, I is equals to 4, I is equals to 5, I is equals to 6. All right. So what we do to find primitive roots, we are actually continuously checking this criteria if this criteria meets. Okay. And the reason we find primitive roots are those specific number that generates this entire sequence up till 6. All right. Primitive roots are those number which generates the entire sequence up till this number, up till this Euler-Tauschen function. Let's say if you have a prime, let's say 23. 23 is a prime number. So the Euler-Tauschen function of 23 is going to be 23 minus 1, 22. So let's try to find out a number. Primitive root is a number that generates this entire sequence up till 22. I don't care about in which order is coming in. I just only care about, will this number generate this entire sequence, this entire number sequence from 1 to 22, whichever order it is. So the checking criteria for this is, we're just checking every single number. In place of I, we're going to use 1, 2, 3, 4, 5, 6, because that's what my Euler-Tauschen function is. And A is also going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, A is equals to be A from all the way up to 1 to 6. Why? Because our prime number is 7. So let's do this. I already solved 1 for you because 1 is quite easy. So here's what we're doing. We're doing this. In place of A, let's take 1. And in place of I, let's take 1. 1 raised to 1 is 1. You take mod with 7, what do you get? 1. Because when you have a number that is smaller, and observe this congruence operator which is there. This congruence operator is there because there's going to be many of these values. many of these values which is going to map to this particular value. Remember in congruence operator when we did modular arithmetic? So let's do this. So in place of a, we'll take 1. In place of I, we will take 1. So 1 raised to 1 is 1. Mod 7 would give me 1. All right. 1 raised to 2. 1 raised to 2 would give me 1. 1 mod 7 is 1. 1 raised to 3 mod 7 would give me 1. 1 raised to 4 mod 7 give me 1. 1 raised to 5 1 raised to 5 mod 7 would give me 1. 1 raised to 6 mod 7 would give me 1. All right. So this is how you're going to generate this. Okay. So let's do number 2. So now what we're going to do is this. Let's say 2. Let's take in place of a, let's take 2. 2 raised to 1. 2 raised to 1 mod 7. 2 raised to 1 is what? 2. Mod 7 would give me 2. All right. So let's do this. 2 raised to 2 mod 7. 2 raised to 2 is 4. Mod 7 would give me 4. All right. 2 raised to 3 is 8. Mod 7. That would give me 2 raised to 1. All right. Let's try 2 raised to 4. 2 raised to 4 is 16. So in place of a, we're using 2. In place of I, we're using 4. So 2 raised to 4 is 16. 16 mod 7 would give me what? 2. 2 raised to 5 is 32. 32 mod 7 would give me 4. 32 mod 7 would give me, if you forgot how we're doing it, so let's say 2 raised to 5 mod 7. 2 raised to 5 is 32 mod 7. So 7 divided by 32. 7 times 4 is 28. And I'm getting a remainder of 4. Hence we have x is equals to 4. 2 raised to 6 is actually 32 64. So 64 mod 7. 7 times 9 is 63. So the remainder is 1. So this is just 1. All right. I hope you're getting it. Okay, so let's do 3. Now in place of a, we have 3. Okay, so 3 raised to 1 mod 7. That is just going to be 3. 3 raised to 2, which is 9, and 9 mod 7. 9 mod 7 would give me 2. 3 raised to 3. So in place of a, we have 3. And in place of I, we have 3 now. So 3 raised to 3 is 27. And 27 mod 7. So this would be 6. We're just taking the remainder and so on. So let me just quickly populate this. I hope you're getting an idea what is it that I'm trying to do here. So let me quickly populate this. So you then I'll tell you which one is primitive root. Okay, so I just actually populated this and just to show you. Okay, let's recap how we're calculating this, how we're fulfilling this criteria, taking a, whatever that number is, which is 4, and raising it to individual powers. So 4 raised to 1 mod 7 would give me 4. 4 raised to 2 is 16 mod 7 would give me 2, and so on. And this is how we're fulfilling this table. So I said the definition of primitive root is a number. Primitive root is the number that generates an entire sequence up till p minus 1. Okay, so the definition of primitive root is a particular number which is a generator that actually generates an entire number sequence in different order up till p minus 1, which is that Euler-Tuition criteria. So if you were to observe this, what value of a is actually generating an entire sequence of that number without repeating itself? within that domain of p minus 1. So if you were to look at it, there are two numbers which are doing this. One is 3, and the other number that is generating this entire sequence is actually when a is equals to 5. If you were to look at this, so let's observe this. When a is equals, okay, so what the primitive roots are, just to recap, is the number that is going to generate this entire sequence up till p minus 1. So since I have a prime which was 7, so 7 minus 1 is 6. So let's look at a. A is equals to 3. When a is equals to 3 is actually generating this entire sequence. Look at it. 3, 2, 6, 4, 5, 1. If I were to continue this further while taking 3 and raising it to 7, after 1, whenever you see 1 after this, the same sequence will repeat itself. Observe this. Let's say, look at it when a is equals to 2. We have 2, 4, 1. As soon as you hit 1, it start regenerating this. So however I take this, a to be 2, and let's raise it to 7, 8, 9, 10. It's just going to keep repeating this pattern. 2, 4, 1, 2, 4, 1. Same thing when a is equals to 4. Same thing when a is equals to 6. All right, so let's look at it. A is equals to 4. Look at it. 4, 2, 1. It's repeating itself. 6, 6, 1, 6, 1, 6, 1. There's only two primitive roots of 7 of p is equals to 7. That is when those primitive roots are 3 and 5. Look, 5 is also repeating the same sequence. 5, 4, 6, 2, 3, 1. After this, if I were to raise 5 to raise to 7, I will get exactly the same remainder as 5, 4, 6, 2, 3, then 1, then it's going to keep continuing itself. So the primitive root for 7 are, primitive roots for 7 are, 3 and 5. These are the primitive root. These are the two numbers which will generate this entire sequence of that number, which is very important in Diffie-Hellman key exchange method. That's why I'm just teaching you this. So a is equals to 3, a is equals to 5. So always remember that this is the criteria you're going to use to generate this. So don't forget to subscribe to my channel. If you have any questions, leave it in the comment section.